Welcome to the ZAG seminar. We're very pleased to have Professor Shing-Tung Yau of Harvard University. And Professor Yau, the floor is yours.
Okay, sorry it came a little bit late because I'm chairing other talks. Today I'm going to talk about some work that I did recently with two younger mathematicians, Tristan Collins and Sebastian Picard, two excellent men from Harvard who used to be our BP, Benjamin P.S. And so today I'm going to talk about Conifold transitions, but before that, we will introduce some general statements first. So a Calabi-Yau manifold would be a complex manifold which supporting a non-vanishing holomorphic n form. It would be one with trivial canonical bundle, but sometimes it just assume the first train class is equal to 0. It depends on the situation. When I say trivial canonical bundle, it implies the first train form is DD bar something. So it is a more refined vanishing of first train class. So, of course, the important case of Calabi-Yau manifold would be Kahler manifold, which has first train class equal to 0. And there we have a Kahler form, which is closed. And these are the Kahler metrics. And the forms are Kahler classes. So a long time ago, more than 40 years ago, then I proved that such a manifold, compact Kahler, Calabi-Yau manifold, there is a unique Kahler metric on X, so that the associated Kahler form has a Kahler class, and so the Ricci curvature of this metric is equal to 0. So that's called a Calabi conjecture. So this has been useful for many other purposes, including in some algebraic geometric discussion for algebraic manifolds, also later for string theory. This was achieved by solving the, hello? Yeah? Any problem? Okay. This was achieved by solving the complex motion pair equation. You rewrite the omega pi, which is a Kahler form you're looking into, to write it to be omega pi, which is omega plus dd bar of some function. And then you want to solve this equation, omega pi to the power n, equal to exponential of some smooth function, omega to the power n. So this is called Ricci flat matrix. If the right-hand side turns out to be the wedge product of two holomorphic, of the holomorphic n form with its conjugate. And this, you can prove that the holonomic group of the metric will contain it SUN. Okay. So this is important for string theory that you can construct a Kahler metric or Riemann metric whose holonomic group belongs to SUN. So when n is equal to 3, that's SU3, which is important for people in physics in string theory. So it was realized around 1984, to be precise, that Kahler Calabi-Yau threefolds give fundamental models in string theory. Of course, before that, people refused to think that it's useful when I talk with them, although I thought that it should be useful. But until 1984, string theory becomes a popular subject, and then they pay a lot of attention to this. And to be fair, I think a great deal of activity starts at that time because of so many people interested in string theory at the time. And this becomes an extremely useful trend of research, studying the connection between Calabi-Yau manifold and theoretical physics, and it has been extremely useful in the past 35 years. So today I'm going to talk, among other things, some ideas from physics that I hope will be useful in understanding Calabi-Yau manifolds that are beyond Kahler manifolds. So non-Kahler manifolds are extremely tough to understand. It has been very difficult because we don't have much tools in understanding non-Kahler manifolds. So I hope some of these works that we are doing may bring in some interesting tools. So, so we are trying to understand what kind of manifold that can be uniformized in some sense. What kind of things could give to canonical geometry? So the question is whether the analog of rigid flat Kahler matrix or non-Kahler Calabi-Yau manifolds. You see, for Kahler Calabi-Yau manifolds, we know the moduli space of rigid flat matrix are given by Kahler cone, because in each Kahler class, we can give rise to a unique Calabi-Yau metric. So it is parameterized by it, and this has been very useful, despite that we have a hard time to write down a metric explicitly. But the fact that uniqueness and existence has been powerful, so that a lot of questions we don't need to know the metric explicitly. So that's comfortable that that is true. But not so clear-cut in non-Kahler manifolds. So let's look at the first important question: what should be a natural generalization of a Kahler metric? Well, the first interesting statement is something called Gottesson metric. This exists on any compact non-Kahler complex manifold, which simply says that there exists a positive 1-1 form alpha, so that alpha to the power n minus 1 satisfies the equation dd bar equals 0. This equation actually is a scalar equation because dd bar of alpha to the power n minus 1 is a top dimensional form. So there's only one equation here. And this kind of equation can be achieved by taking a conformal change of alpha. So given any positive 1-1 form, you simply multiply it by a function. You can prove without much difficulty that this equation can always be achieved if you multiply it by a positive function, and this can be proved to be true. So this was observed by Gottesson many years ago, probably 50 or something years ago. And so these are useful fact, but it's not canonical as Kahler manifold. As you see, any positive 1-1 form can be deformed conformally to such a metric, and they are infinite dimensional, so there's too much freedom. So we need to try to find some way to cut down the freedom. Well, then there's a stronger notion called balance metric. This was introduced by Mary Louise Michelson in 1970s, I think. And this metric is interesting for many purposes. So a metric, a Hermitian metric, G is called balance if the 1-1 form alpha satisfies the much stronger condition that alpha to the power n minus 1 is a closed form. So this is far stronger than the dd bar of it equals 0, because dd bar of it equals 0 implies it is a scalar equation. But d of alpha to the power n minus 1 equals 0 is a vector value equation, because d alpha to the power n minus 1 is a n comma n minus 1 form. And so this is more equations than the first equation. And therefore, naturally, this metric do not always exist. So it is, on the other hand, is clearly true for Kahler metric. So Kahler metric has a property d alpha equals 0. So this d alpha n minus 1 equals 0 is automatic. And this is stronger than the Gottesson metric because d of it equals 0 implies dd bar equals 0. So it is between the much weaker condition of Gottesson compared with the Kahler metric. So Mary Louise Michelson gave a good characterization what a balance metric exists mean in terms of current on a complex manifold. Those current criteria, it sounds very neat, but it's actually difficult to be used in a concrete situation. But nonetheless, it was proved by two mathematicians, Alessandrini and Bassanilli, so that the existent balance metric is invariant under birational transformation. This is a very remarkable property. Namely, if a complex manifold admit a balance metric, then by blowing up and blowing down of the manifold, that means going through birational transformation, the manifold will still admit a balance metric. So the existence of balance metric is invariant under birational transformations. This is a very remarkable statement because this is not true for Kahler metric. You could have a complex manifold birational to a Kahler manifold, and yet it does not admit a Kahler metric itself. I think the first example was given by Hiraka. So balance metric, therefore, should be useful for birational geometry because of this remarkable fact. But not that much has been done in this direction still, but it shows the potential use of the concept of balance metric. So therefore, it's natural to ask if a version of the Calabi conjecture holds for either quadratic metric or balance metric. So namely, does a non-Kahler Calabi-Yau manifold admit a quadratic or a balanced Chern-Ritchie flat metric? So what it means, Chern-Ritchie flat, because we have different connections on a non-Kahler manifold. On a Kahler manifold, all the connections are the same, so you don't have to specify what connection you use. But there's, in the case of non-Kahler manifold, there's several connections. So there's a Chern connection, and we are talking about using the Chern connection, the metric, the Ritchie curvature equals 0. So Cortisone, after the Calabi conjecture, make a proposal that the Chern-Ritchie flat Cortisone metric with the first Chern class equals 0 should exist. Now, when we say first Chern class equals 0, we always should remember that for non-Kahler manifold, what it means is equal, the Chern form, the first Chern form is equal to dd bar of something. So it means vanishing in dd bar cohomology. So this is much stronger than to say that it vanishes as a cohomology class. Vanishing in cohomology class for non-Kahler manifold is too weak, not much use of using that statement. So we have to make sure that it vanishes in dd bar cohomology. So several of my friends, Satakidi, Tosati, and Renkov, proved that the answer to this question is yes. The proof is non-trivial, although they are following the line of the proof given in the Calabi conjecture by me, but still there are many non-trivial steps that needs to be taken care of. So they show that every compact Calabi-Yau manifold with first Chern class equals 0 in dd bar cohomology, BC means both Chern class, admits a quadratic metric whose Chern-Ritchie curvature equals 0. So this is rather remarkable and solve the problem that Godison proposed, but it's not clear this canonical metric, how canonical this metric is. I think it's not canonical into the sense that we hope to see. Namely, I think the moduli space of such metric is not finite dimensional. And therefore, there are more to be desired to use this non-Kahler Calabi conjecture. And the reason is that the Godison metric is too big, infinite dimensional, way too big, I think. So more natural way is to make the metric more canonical, is to require the metric that we use is balance. So balance, remind you, is alpha to the power n minus 1 is closed. So in a way, this is kind of due to the Kahler metric condition where we ask d alpha equals 0. And of course, we can say more things by minimizing among the metric, we can minimizing some Yang-Mills functional and all that, but we are not so sure yet. But anyway, so we want to look into a question which may be interesting for Kahler manifold itself also. So the question is to try to understand Kahler and non-Kahler Calabi-Yau manifolds. What is the relation between them? So you recall a fundamental open question is to understand all possible topological types of Kahler or projective Calabi-Yau manifolds, 3-dimensional, let's say. And today we already know by using computer search, there are a huge number of them. Just in terms of hot diamond, there has been 30,000 distinct things, probably much more than that, at least that many. So this becomes a problem for string theories, and they call it a landscape because there are too many vacuums that appears in string theory. And then it was proposed by several people that actually all the Calabi-Yau threefolds, despite their different topology, it can be connected by operation called a geometric transition. So they said, okay, there are many of them. We are allowed to deform it in some way in string theory, but there are different topologies, difficult to deform in the standard sense. So we like to deform it in a more exotic way. So this proposal was developed by several mathematicians, started by Clemens, and later worked out by Friedman, Bob Friedman, and my three call it Reid's fantasy. Somehow, I think he did not want to say that he make a conjecture on such a statement, so he called it fantasy. In the physical literature, actually, similar proposal was made by three of my friends, Candelas, Paul Green, and Tristan Hoops. In fact, Tristan was my postdoc. So the important example is this: a geometric transition is the Conifold transition obtained in the following way. So let Y be a smooth Kahler Calabi-Yau threefold that contains a collection of mutually disjoint smooth curves. Each of them are P1 rational curves, and each of them has normal bundle isomorphic to O-1 plus O-1. So these are rigid curves. These rigid curves has a property that it can be brought down to a point. So each EI can be brought down to a point. So contracting them, we obtain a singular Calabi-Yau threefold, X0 we call it. And each point would be an ordinary double point. This is a well-known thing, that a rational curve in normal bundle isomorphic to O-1 plus O-1 will be contracted down to rational double points. So as a result, the manifold minus the union of all these curves is isomorphic to a singular Calabi-Yau threefold minus points. Okay. So now, for this singular manifold, there are interesting, important statements. And this statement, first important statement, was found by Robert Friedman. He demonstrated that you can smooth the X0 out. X0 itself is a singular manifold with rational double points. So the question is whether you can smooth it out to be a smooth manifold. And he says that the infinitesimal smoothing has the obstruction coming from the following way. If the classes EI, the rational curves, which is an element, look at it as an element in X2 of the manifold with coefficient in omega2, so X2, 2, is that if those classes satisfy a relation, a non-trivial relation, summation Ni EI equals 0, where not all the Ni are 0. And so all the Ni are not 0, and satisfy summation Ni EI equals 0. So this is non-trivial relations between the EIs. So Bob Friedman proved that if the EI satisfy this condition, then we can blow it down and we get a singular Calabi-Yau manifold, and we can have an infinitesimal smoothing of the resulting singular manifold. So that's what Bob proved. And then later, Kawamata and Tan proved that the infinitesimal smoothing can always be realized by real smoothing. X0 can be smoothed to a family of smooth complex manifold, XT. So this is good. So now, given a Calabi-Yau manifold Y, we blow down several curves, rational curves, which are rigid, and then if satisfy the Friedman condition, we can actually smooth it out to a family of smooth complex manifold, XT. So we get a smooth complex manifold we call XT. Since EIs are only curves, XT are still Calabi-Yau, so the holomorphic and free forms are still there. And it has the properties that was observed by Friedman. The pi1 of XT is the same as pi1 of the original manifold Y. And in a way, it's reasonable, obvious, because the EIs are complex codimension 2. So the fundamental group is still preserved. The canonical bundle of XT is also trivial. So there exists holomorphic free forms on XT. So it is Calabi-Yau in that sense. And a much more subtle statement was the DD-bar lemma holds on XT for general T. Actually, I also always curious about this statement because in the old, 20 or 30 years ago, when Friedman wrote his paper, he said that it's rather obvious. But this was finally written up in more detail in about a few years ago. So DD-bar lemma holds on XT for general T. So this is good. So XT enjoys interesting properties. It is nice pi1, so finite. Canonical bundle is trivial, and the DD-bar lemma holds for this general T. So now, given a Y, we have this transition. It blows down to X0 and moves to XT. And the XT has trivial canonical bundle, but in general, XT are non-Kahler. And it's obvious that it's non-Kahler in most cases because the curves, for example, EI could generate the second homology of the manifold. And I kill them all, it produces a manifold with trivial second homology. So if the curves generate the second homology, I obtain a manifold XT, which has no second homology. And what that means is that it's not Kahler in particular. Kahler manifold, the second homology is non-trivial. So by using the work of CTC Wall and all that, one can prove that in many cases, you can obtain Cornet sum of S3 cross S3. So these are interesting donuts, except it's in complex 3 dimension. It's similar to the Riemann surfaces that we see. Riemann surfaces are donuts, several handles put together. So we are talking about real 3-dimensional handles, Cornet sum of them. So in this way, one can prove that one can construct complex structure on such Cornet sum of S3 cross S3. So Cornet sum of S3 cross S3 looks very simple in topology. On the other hand, it seems to be completely non-trivial from the viewpoint of complex manifold. You see, we can produce a lot of integrable complex structure on them out of Calabi-Yau manifolds. So this is a good construction. And Reid, what he called the fantasy is that all Kahler Calabi-Yau threefolds fit into a single universal moduli space in which families of smooth Calabi-Yaus are connected by Conifold transistors, and or their inverse, even though they could be of completely different homotopy type. So I guess Reid does not want to say it's a conjecture because it seems to be amazing if it's true, and because then all the Calabi-Yau threefolds, despite they have different homotopy type, they are connected together in a nice way, and hopefully this can be resolved many questions or puzzles that string theories like to see to be solved, because now they are connected together. At the same time, Paul Green and Tristan Hobbs found that for a very large number of distinct Calabi-Yau threefolds, the relevant modular space drawn together to form a connect web by including certain singular limit space. Then Candelas, Paul Green, and Tristan Hobbs studied the geometry of this modular space, especially near the interfacing regions which corresponding to conifolds. So this were interesting, and they also showed that the Wade-Peterson metric coincide with the point field limit of the semological metric, and all the distance in the web are finite. So Candelas, Green, and Hobbs has been studying Wade-Peterson metric a long time ago, I think before the mathematicians of the Calabi-Yau modular space, and they did beautiful work on this direction. So now we like to understand from the point of view of geometry, differential geometry, and because we like to understand what the modular space of this whole thing is. So we like to know in the conifold transition from y to x0 to xt, what kind of things are we moving, the Calabi-Yau metric? In the case of all Kahler Calabi-Yau metrics, we have nice modular space, Kahler modular space, and also complex modular space, and they define a nice, beautiful picture for Miller symmetry. But here we have to understand much more. Okay. So if they, of course, xt sometimes could be Kahler if you you don't not necessarily Q order homology. In the case when it is Kahler, they actually you need rigid flat Kahler metric in each Kahler, each class, and then we can study the modular space using this rigid flat matrix. But now the conifold transition, in case xt is not Kahler, it is no more in Kahler geometry, and we need an analog of Calabi-Yau metric in the non-Kahler setting. And that's what we are looking for. So this has actually is a driving force for me for many years to try to understand what is going on for non-Kahler geometry, especially on this class of naturally construct non-Kahler manifolds. Okay. So from very beginning, actually, in 1985 or 1986, when the compatification due to Candelas, Strominger, Witten, and Horowitz come up, where they take the sixth manifold to be trivial product with the Minkowski spacetime. And this Strominger was talking with me, and he proposed to use a walk product instead. So he come up with a system which is a natural candidate of the Calabi-Yau matrix. At that time, I did not know that Chris Hall also worked on this system independently. So now we call it Hall-Strominger system. So these are the natural candidate for compatification and is motivated by string theory. So we look at this compatification of superstring theory, and as I said, what they do at the beginning, due to four authors, Candelas, Horowitz, Strominger, and Witten, they construct a metric product, just trivial a product of the four-dimensional spacetime, Minkowski spacetime, or Massimo symmetric four-dimensional spacetime of, say, anti-de Sitter and all that, with a six-dimensional Calabi-Yau vacuum, and this form of 10-dimensional spacetime. But now we can use a Trish product. And at the same time, when you do this, this metric construction, I actually propose to Ed Witten to use the work that I did with Simon Donaldson, and well, Simon Donaldson independently, and Ken Rubin and I, construct Hamilton-Young-Mills connection over stable bundles. So I was proposing to use this one for doing heterotic string theory. So at the beginning, actually, Ed Witten does not believe that is useful, but then later he and Horama Witten proposed to use higher rank bundles for strong coupled heterotic string theory so that the gauge group can be SU4 or SU5, so more than just SU3. So this turns out to be a rather fundamental observation later when we talk about heterotic string. Well, so as I said, Chris Hall and Andy Strominger independently try to understand heterotic superstring background with spacetime supersymmetry and non-trivial torsion by allowing a scalar walk factor for the spacetime metric. So instead of a trivial product between the Minkowski spacetime and the Calabi-Yau manifold, you allow a non-trivial walk factor. And this changed the geometry on the 6-dimensional manifold. At the beginning, when you take a trivial product, supersymmetry makes sure that the 6th manifold is Kahler. But now, because of the introduction of a torsion factor, the 6-dimensional manifold need not be Kahler anymore. It becomes a non-Kahler Calabi-Yau manifold. So let me describe how it comes out. So this non-Kahler Calabi-Yau manifold will be an important role in discussion since they can be used to construct string theory with fluxes. So this interesting. So in the standard compactification, there's no fluxes, but now there are fluxes. The non-zero torsion give rise to some non-trivial field in heterotic string theory. So the flux will turn out to be determined by a free form. So in string theory, there's a free form, which in the case of Kahler manifold, we take it to be trivial. So it is equal to square root minus 1 d minus d bar omega. So this is a real free form. It's important to understand what flux means in heterotic string. And this, we took it to be trivial when the manifold is Kahler, because omega is closed. But now omega need not be closed, therefore H could be non-zero. So now the free form is non-zero. We need to find the equation of motion for supersymmetric compactification of heterotic string theory. So they independently derive the equation based on space-time supersymmetry consideration. So you take the space-time obtained by walk product of Minkowski space-time with the 6th manifold, and you study what the space-time supersymmetry should mean. So they consider the following walk product. So you see, the G0 is a product metric on M cross X, except it's not complete product. I allow a conformal factor in front of it. It's exponential 2dy. And y depends only on the 6-dimensional manifold, the internal space. So there's an answer they proposed. They said, let's take this metric. It's a trig product, and it's not a trivial product. And just d is now no more trivial, not constant. This is sometimes called dilaton later, dy. And let us assume, because we are talking heterotic string, we allow there exists a bundle, turns out to be holomorph bundle also over X, over the manifold, complex manifold X, which turns out we would also ask them to satisfy a Hermitian-Young-Mills connection. And so this will be a connection which satisfies supersymmetry. So this condition has the property, the curvature of it, wedge omega square is equal to 0, and the 2 and CO2 part is equal to 0. So these are Hermitian-Young-Mills connection on the bundle, on the manifold X. And so here omega is the Hermitian metric defined by the metric Gij bar. So this equation, of course, we know how to solve actually. In the case of when the metric is Kahler, this was the work due to Ken Rubenberg and myself. When the metric is only Cartesian or balanced in this case, this was solved by Jun Lee and myself a few years later. So, this equation 1 can be solved because the work that we knew on Hermitian-Young mules. So at the beginning by Ken Rubenberg and myself, and later by Jun Lee and myself. So the system we are going to deal with, which we call Hall's geometry system, is that we write down several important quantities. The first quantity is a free form, which we call flux, h equal to square root -1 d bar minus d of omega. And phi is the dileton that we are talking. And so it is the norm of omega. Omega, capital omega, is a holomorphic free form. There's a natural metric on this free form. It is the norm of omega, coming from the Hermitian metric omega. So this is the quantities that appears in physics and appears in geometry. In order for the ansatz proposed by Hall and Strominger to form a supersymmetric configuration, one introduces a spin law, epsilon, and this should satisfy these three equations appear in physics. One psi m is gravitino, lambda is diletino, and chi is a Gruano, and phi is a dileton, and h is the field strength obeying this equation. So all these are conditions satisfied by the demand of supersymmetry. So naturally come out. Alpha pi is the string tension. So perturbatively appears there as an anomaly condition. So the outcome is this bottom equation, dx equal to alpha pi over 2, second transform of the bundle, which is f wedge f, trace of it, and the second transform of the manifold, r cross r, trace of it. And it's supposed to be dh, where h is the d bar minus d omega. So this is the equation linking omega. Omega is the Hermitian form with the bundle. The right-hand side is defined by the bundle, F. And R is the Hermitian metric, is the curvature coming from small omega. So this is the equation linking the metric, Hermitian metric, on the base manifold with the bundle metric. Now, this automatically gives rise to a constraint, namely the second train class of the bundle is equal to second train class of the tangent bundle, because trace f wedge f is the second train class of the bundle, and trace r wedge r is second train class of the manifold. The left-hand side is dh, in fact, it's d bar of omega, and therefore these two train classes are equal to each other in the broad train classes, broad train cohomology. So this is a necessary condition for the manifold, for the whole setting to satisfy the Hall's geometry system. So what do we have? So the first equation is number 1, namely the bundles satisfy the Hermitian-Young connection with respect to omega. And then the second, the last equation here has the whole, is called the anomaly equation. Alpha pi is supposed to be small because the corresponding to the tension is to be small. Okay, now we still need another equation is coming from space-time supersymmetry. Turns out, in order to manifold with holomorphic form, first of all, there's an anomaly cancellation, which is the last equation I mentioned, namely equation 2, I just wrote down, the same equation as the previous one. But the supersymmetry turns out to require one more condition. So let me remind you what supersymmetry is. Supersymmetry is simply these three equations in the middle of this slice. So there's a spinor sets around all this, and then you do some calculation, ends up to demand of some equations. Supersymmetry require d star omega. Omega is the Hamilton form. D star omega is equal to the middle one. So this was what was written by Strominger and Hall. And this actually looks a little bit complicated. But then Jun Lee and I observed that this actually can be rewritten in a much more neat form, namely equation 3. So capital omega is holomorphic free form. The norm of it with respect to omega times omega squared is closed form. So this is very nice because what that means is that capital omega norm of it times omega squared defines a balanced metric. This is exactly what balanced metric means. So small omega after conformal change becomes a balanced metric. So what is the end result? The whole small Schrödinger system comes from three equations. The first equation is number one here, that the bundle satisfies the Hamilton-Young-Mills connection. The second equation comes from number two here, that it satisfies the C2 of the manifold minus C2 of the bundle is equal to d bar omega. So it links omega with bundle. And number three says that omega, small omega, after conformal change in a nice manner, it becomes balanced. So these are the equations that we want to solve on a non-Kahler complex manifold. And this is called Hall-Schrödinger system. We call it so. And this is the question that how can we solve it? And this is a system now with non-trivial dilettante field and a Young-Mills field. So different from the standard Calabi-Yau theory, where the dilettante field is set with 0, and dy is trivial also. So this becomes a fascinating statement. It's a system of equation far more complicated than the original Calabi-Yau equation. And so the question is, can we solve it? Actually, for a long time, we don't know a non-singular solution exists. Any Strominger tried to look into it, but he gets singular solutions with some delta function and all that. It's not quite satisfactory. So I talked with him for quite a long time until I finally realized that we can construct smooth solutions. So these are works with Jun Lee and with several other people. And so equation 4 is a restrict holonomic equation, which can be viewed as analog to the complex Monge-Hamilton equation appearing in the Calabi conjecture. And equation 5, as I said, is a similar equation to duy in the Kahler setting, and the Li-Yau, Jun Lee, and myself in a non-Kahler setting. And last equation 6 is so-called anomaly cancellation equation, where alpha pi is a constant, it's a non-trivial but small constant. This is the important equation that linking 4 and 5 together, because 4 and 5 are completely independent of each other if you just look at it by itself. But 6 is the one that links 4 and 5 together. So it becomes a highly nonlinear equation, link them together. So this becomes a highly nonlinear system of PDEs, and this has been unknown for a long time how to solve it in a general setting. So I conjecture for a long time that solvability is equivalent to stability of the gauge bundle and all that. The conjecture is still far away from being solved, but nonetheless, there are many important progress into here. So first of all, we need the manifold to be a balanced manifold, because this tau is actually a closed form, 4 form in the manifold, which is closed and positive. And then it turns out we want the bundle to be stable with respect to tau. You can define what stability means for such a balanced manifold also. And the cohomology condition is also a necessary condition, which I said. So let me tell you what is known about these things so far. So first of all, this should be looked as a natural generalization of Calabi-Yau condition from Kahler geometry to non-Kahler manifold. We can simply take the bundle to be a holomorphic tangent bundle to the gauge bundle and set omega equal to h to be the Calabi-Yau manifold. Then you will reduce to the Calabi-Yau manifold at the very beginning, and so this generalizes the Calabi-Yau condition from Kahler manifold, non-Kahler manifold, by simply taking the bundle to be the holomorphic tangent bundle and the metric to be the rigid flat metric. Now, this is the case when the manifold is Kahler, and we can do things by small perturbation of the Kahler manifold. This was done by Junli and myself, but that's not good enough. We like to study non-Kahler manifold. So here, in the case of Kahler Calabi-Yau, Junli and I study more than just tangent bundle. We take the tangent bundle plus some trivial line bundles. So if we are interested in R equal to 1, that will correspond to SU4, R equal to 2 corresponds to SU5. So it goes from a SU3 bundle to SU5 bundle. And under suitable non-degeneracy condition on the Kodaira-Spencer class of the deformation, we get interesting solutions. So Junli and I perturb the bundle, which is tangent bundle plus a trivial bundle. And this gives us interesting statements about, say, smooth printed freeform. We found a large class of interesting examples of regular irreducible solution to the Horst-geometry system with gauge group U4 and U5. And this was extended by several authors in Spain, Andras, Garcia, and Fernandez, nicely. But the first non-trivial non-Kahler case was done by Fu and myself, Fu from Fudan University. These are T2 bundles over KV surface, constructed by Calabi-Yau method, and several other physicists was involved later, but the original come from Calabi-Yau. So these are T2 bundles, and the T2 is actually a no moduli in this case. And it turns out the Horst-geometry system could be reduced to a very complicated nonlinear PDE among Monge equation for a function defined on the KP surface. And this, we worked rather hard actually to get a good estimate up to third order and then use the continuity method to solve the equation. These together led to solution of many non-Kahler solutions to the Horst-geometry system, making use of some theory due to Mackay for stable vector bundles on KP surface. So KP surface, a lot of these questions are understood by many different algebraic geometers. Now, but actually, a class of compact non-Kahler Calabi-Yau freeforms was constructed by Calabi many years ago, and using triple periodic minimal surface in R3. And this construction was later generalized by Gray, Alfred Gray. And the Calabi-Gray manifolds are total space of certain non-trivial holomorphic vibration whose fibers are hyperkähler 4 manifolds. And these are rather interesting manifolds. The base are triple periodic minimal surfaces. And my former student, Ten Fei, generalized this construction, and working with several people, Wang and Picard, they showed that the full Horst-geometry system can be solved on a large class of generalized Calabi-Gray manifolds. So they produced many interesting non-Kahler Calabi-Yau freeforms. And interesting enough, These are unbounded topological type. They have infinite number of topological type and Hodge numbers. So I believe many of them are not probably not physical, hopefully. Otherwise, we have infinite number of vacuum in string theory, which I don't believe. Okay, now let's come to the recent work, which I did with Tristan Collin and also Sebastian Picard. So we come back to the Conifold transition. Now, the original manifold has a Ritchie-Kahler, Ritchie-flat manifold. We are looking at the Conifold transition. So we are looking at the case of a matrix. So the Calabi-Yau matrix give rise to omega t and ht, and we are looking at pair Hamilton matrix, and we look at the equations, and we come out with this. If omega t equal to ht, ht is on the bundle, then the system implies omega t is Kahler-Ritchie flat, which we assume not to be so. The first equation of the system, namely the balance condition, was actually solved by Fu, Junli, and myself about 6 or 7 years ago. This is actually rather non-trivial fact, which we found. So we proved that given a smooth Calabi-Yau manifold, we do the Conifold construction. Then for sufficient small t, xt admits a smooth balance metric. Now, this is a rather non-trivial statement that such a manifold admits a smooth balance metric. And it takes a lot of work that we finally come up with this construction. So in particular, we proved there exists balance metric on the connect sum of S3 cross S3 for any k bigger than 2, bigger than or equal to 2. So these are complex structure on S3 cross S3 to connect sum. So this in contrast to the question about S3 cross S3. The manifold there are non-Kahler, and we are not sure what happens in that case when k equal to 1. So the local model is simple. You take a small resolution. So you take the first column is the P1. You get O minus 1 plus O minus 1. And the small neighborhood give rise to S3 and all that. And the radii in this way, we using a bundle metric is 1 plus D. D is in P1. U squared plus V squared is in the bundle. And we look at no neighborhood by taking R squared less than C. And then we broke it down to a point, the P1, and it's in the middle. And the middle one is the double point, which we turn down there. And we smooth it, deformation. The local model says that equal T. And this is nice. You get to a non-singular manifold when you have small neighborhood. And there we have a symmetric construct by Canderas and De La Osa. And these are integer metric by taking DD bar of F naught of R squared and FT of R squared, where F naught of R squared is by definition a function R to the power 4 over 3. So using R defined in this separate representation, in the case of a bundle, I mean O plus 1, O minus 1 plus O minus 1, we use that R, but it's the same as this residual double point here. So then we define FT R squared by using this bottom condition. Then it turns out this defines a Kahler metric, Calabi-Yau metric on the local model. So what Fu and Junli and I did is to construct a declosed positive 2-2 form on XT for sufficient small t. First, the way that we do it, we first construct balance metric on a singular Calabi-Yau manifold X naught by gluing the square Calabi-Yau metric, namely omega square on Y, to the Canderas de la Osa metric near the nodes. So this rather delicate construction by gluing two metrics together. And the whole point is, of course, you can glue metric together easily if you don't care about what condition it is. Here we want it to be balanced. So after gluing is a balanced metric. This yields a declosed positive 2-2 form on the X naught minus pi. So the x naught take out the pi's. And then we grew the Candelas-Dirac-Oza metric without t there on the deformation to omega to get real d closed 4 form phi t there. And phi t is now is a d closed 4 form, is a real form. It can be decomposed into 3 parts, 3 1 part, 2 2 part, and 1 3 part. And because t can be made to be small, is a deformation. And since phi t is positive definite, we can make phi t 2 2 to be positive definite. But phi t is no more closed. So phi t was closed, but phi t 2, 2 is no more closed. So we have to solve a fourth order equation with some estimates. We show phi t 2, 2 can be perturbed to a closed positive definite 4 form when t is sufficiently small. So this is actually a hardware to do all this. So by taking the square root of such a 4 form, we obtain a smooth balance metric. So this procedure allows Jun Lee and Fu and myself to find a balance metric on the Conifold transition. And this is very good because it's the first time we have a structure, non-trivial structure, on the Conifold transition. So now, once we have this balance metric, which is obtained by Fu, Lee, and myself, we have a balance condition, and then we can consider the Hermitian-Yang-Mills equation with respect to this omega t. As I said, Jun Lee and I was able to solve the Hermitian-Yang-Mills condition on any quantitative metric. So in particular, we can do this. Now, in my other student, Chen, thesis, about, I don't know, 8 years ago, he constructed Hermitian-Yang-Mills connection metric xt, solving this equation, fxt wedge omega t squared. And on holomorph bundles, which are deformation of bundle, which is stable with respect to y, omega cy, the Calabi-Yau form. But here assume it's holomorphic trivial in the neighborhood of the contract curves. So he requires the bundle to be trivial there. The estimate that Fu and Lee, Jun Lee, and myself play a key role in Chen's work. The most natural setting to consider Conifold transition is when the holomorph bundle in the Horst geometry system is the tangent bundle, because we like the second Chen form to be the same at the bundle with respect to the same as the tangent bundle. It is not quite, it's not holomorph trivial on the -1 curve, so we have to improve Chen's freedom to the more general case. So that's what Tristan Collin and Sebastian Picard and I did recently. We proved that when t is small enough, there's a Hermitian metric on the tangent bundle of xt, solving this Hermitian-Yang-Mills equation, where omega t is a balance metric that Fu and Lee and myself did, where ft denotes the curvature of the Chen connection with respect to xt. This result shows that in particular, we can solve number 7 simultaneously. And also we give estimates showing that at least near the ordinary double point singularity, the pair of metric omega t, ht given in this way approximately solve the whole geometry system. Now, so the question is what happens and whether we can actually solve it. So at a suitable small scale, omega t, ht converges to Kahler solution of the Horst geometry system on the Conifold given by the Candelas-Dirac-Oza metric. So we need to prove that, and we could do it by the proof in the following way. Step 1, we construct a Hermitian-Yang-Mills metric on H0 on the regular part with respect to the balance metric constructed by Fu and myself, and Lee, Jun Lee too. And then this is achieved by studying a family of smooth balance metric omega alpha on y for alpha small, so that omega alpha is approximate to capital omega naught. Since the tangent bundle is stable, which we use the Calabi conjecture to prove, then we can prove that this, we can generalize the generalization by Junior and myself and of the DUY theorem to the Gottesson metric, so that we can find Hermitian-Young metric H alpha with respect to omega alpha. And then we prove that the Hermitian-Young metric converges smoothly away from the -1 curve to a Hermitian-Young metric on the tangent bundle X0. The important thing is that near the singular point pi of X0, the metric X0 converges to a polynomial ray to a multiple of the Candela-Stellar Osa metric, and this is very important. Step 2 is that we glue this metric X0 to the Candela-Stellar Osa rigid flat metric on a smooth conifold. Precisely, we fix compact sets Ki on X containing an ordinary double point of X0, and we use a diffeomorphism mapping the complement of Ki to Ht minus Kit, where there are compact sets containing a vanishing cycle of Xt. And then we look at the pullback of the H0. The one part is approximately Hermitian-Young on Xt with some error, which we can estimate. And then we glue this metric back to the Candela-Stellar Osa rigid flat Kähler metric on a smooth conifold to get approximately Hermitian-Young metric on Xt with explicit estimate for the error. So all these estimates are important to be used. And for t sufficiently small, this metric can be perturbed to give a genuine Hermitian-Young metric on Xt. And then we can complete the whole system by understanding the anomaly cancellation equation. And this is the Ht that we need to understand. And this, we have to do several approximations. And this is done with a lot of estimate, which is outlined in these two inequalities down here. So we therefore expect the solution of the Hall geometry system on a pair X with tangent bundle, holomorphic tangent bundle can provide canonical metric, which is continuous in opposite sense through conical transition. So this is what we can do, which I think is rather amazing in many ways, because I always would like to see a canonical system of metrics to be on non-Kähler manifolds. And this Conifold manifold, although it is not too far from Kähler, is related to it, we actually can give some interesting, important system on it. So this work of fully Clemens and Picard and myself, I think, give evidence that we can give nice structure on this manifolds. And I hope eventually we can learn much more on string theory about these things, or even for algebraic geometry. And in fact, ordinary double point is not necessary. We can obtain singular Calabi-Yau with singularity model on more general singularities. And this can be done, and which we shall publish sometime soon. And I think I will stop here. There's sympathetic version of this whole thing, which I don't think I have time to get into. But so I will stop here now.
All right, let's thank Professor Yao. So I'm going to turn off the recording, and then people can ask questions.
Yeah.
So